So remember, we've already dealt some with rational functions. We're going to do a bit more detail. Remember, we had some vertical asymptotes, right? Yeah, we're seeing some graphs with those. And in behavior, we dealt with that a little bit, right? Sound familiar from chapter 1? So we're going to look at rational functions of the form f of x equals ax to the n plus bx to the n minus 1 plus whatever else is happening over there, divided by px to the m plus qx to the m minus 1 plus whatever else is happening over here. If you may notice, we are looking at primarily only the highest exponent part. So this part is the only part that really matters, assuming these are polynomials. And I'm going to put one more thing out here, plus k. Note that k is not part of the rational function, so it's not a constant in this. It is outside the fraction. So, do you remember what an asymptote is? If you want to do volunteer definition. Yeah.
It's like on a graph, the numbers that go on.
Never touches is not a good term, but approaches. It approaches in the long term. So we saw graphs that were like this, where this, if we went to infinity, this approaches 0, doesn't get there, but it does approach it. Now, the reason I think doesn't touch is not a good representation, because you can have some graphs that do this. Come up, cross it, and then approach from the top. And it would touch it there. But it still could be an asymptote. But there's also ones that look like this, where we have ones that go back and forth across it, getting closer and closer. Which would be a like sine cosine graph if you were that from last year in algebra 2. So doesn't touch is an idea, but what it approaches in the long run. So note, this, like if we look at the first graph I did up here, you ready? All the stuff. This has a vertical asymptote and a horizontal asymptote. So we're going to be looking at what causes those, or what features to look for. You get them. So first we're going to do the horizontal asymptote. Okay, that's the easier one. Well, somewhat easier. Horizontal asymptote. If m is greater than n. So we look at here, we have a function where the bottom, the greatest power on the bottom is greater than the greatest power on top. So you could say x to the third plus whatever over x to the sixth plus whatever. So the power on the bottom is bigger than the power on top. What does the graph go to in the long run? Or what is the end behavior of this graph? If you look at this part, what's the end behavior of this, just this part right here? You're plugging a really big number for x. What's going to happen to this? What? 0, good, yeah. And you have a million, like a million to the third divided by a million to the sixth. You get 1 over a million to the, 1 over a trillion, quadrillion, something like that. Basically 0. So you add 2, and what do you get? So this is what I talked about when I talked about the end behavior. So if we have this form, we get the asymptote x, actually I'm going to change color to make it stand out a little bit, x equals k. So whatever k is, that's what our asymptote will be. That is if the power on the bottom is bigger than the power on top. So in this case, with this function right here, it is x equals 2. We have a horizontal asymptote at x equals 2. Anybody question on that? Fairly clear? Second case, we're going to put if m equals n. So we would have a 2x cubed plus 5x, whatever, plus, and then the x cubed plus minus 6x squared plus whatever. The power on top is equal to the power on the bottom. And I put plus, and I'll 1. Anybody remember what you do for this? We talked briefly about it. What? Okay, you multiply what?
You add maybe to the top.
Okay, close. So you do x equals a divided by p plus k. So you got plus k plus.
Yeah.
So notice, we take the coefficient, divide them, so notice the coefficient here is 2. What's the coefficient on the bottom? 1. So 2 over 1 plus k. So in this case, it would be x equals 2 over 1 plus 1, which is 3. So we get x equals 3 in this case as our coefficient. I'm going to make sure it's clear. So the goal is you take your coefficient on the top, divide by the coefficient on the bottom, and then add whatever constant you have. Everybody clear on that? Remember, this is what we were talking about when we were talking about end behavior of the graph. So when we have rational functions, end behavior is what you're asking for. So you have m greater than n, m equals n, what will be the next one? M is less than n. In other words, the power on the top is bigger than the bottom. Anybody have a guess what you do? Anybody? So which is growing faster, top or bottom? Top. So let's say if you had a billion cubes divided by a billion, what do you have? Billion cubed divided by a billion squared. Now if I put a bigger number into that, is it going to get bigger or smaller? A trillion? So in this case, no horizontal asymptote. So anytime the power on the bottom is smaller than the power on top, you do not get a horizontal asymptote at all. Now I'm going to put a little note here. It's not as important, but you can get slant asymptotes. Slant or oblique. Slant or oblique, these are two terms for the same thing. Asymptote. So if you are looking for a slant or oblique asymptote, it is a special case. M plus 1 is equal to n. In other words, the power on top is exactly 1 more than the bottom. So f of x equals x cubed plus 2x squared plus 5 over x squared minus 7, something like that. Where the power on top is exactly 1 more than the power on the bottom. What this gets is in the long run you get an asymptote or something that looks like this, where you might have a curve, but it's going to a line here. And on the other side you might get a curve that does something like where it's approaching a line. These ones, you get a line that goes to 0, or goes to k, whatever it is. Where you have your line here. If you have this one, again it would look the same way, just shifted. This one, you might get something that looks like this on one side where it's going up infinitely, and that on the other side, you might get something like that. But it doesn't approach any line. Instead, so this one, it approaches a line. Now, to actually figure out what that line is, all you do is do synthetic division or long division with these two functions. And whatever it simplifies to, without your remainder, is what your line would be. I don't think there's any in the homework to have you do that, but that's what the process you go through. Any questions on that? Yes, no, maybe. Okay. The second part. Does this deal with horizontal? What do you think we should talk about now? Vertical, yes. So I'm going to put the form f of x equals a of x over p of x. So in other words, in these cases, we're not talking about ones that have k, because k complicates things a little bit. We're going to have three cases. If you have p of x equals 0 and a of x does not equal 0. I'm going to say values where p of x equals 0 and a of x does not equal 0. In other words, the denominator can equal 0 at a point where the numerator cannot. So let's say f of x equals x minus 3 over x minus 5, x plus 2. So locations where the denominator can equal 0 and the numerator cannot equal 0 give vertical asymptotes. So what would the vertical asymptotes of this function be? X equals 5, x equals negative 2. Hold on. Back here, I think yes, I do something. These should be y equals. Y. Because it's a horizontal line. Yeah, my mistake, I am sorry about that. I should have y equals on all of those. Not x equals, we're talking about a horizontal line. Everybody fix that? Okay. Okay, these ones are going to be x equals. So we'd have x equals 5, x equals negative 2 would be your vertical asymptote. Now, next case. Values where p of x equals 0 and a of x equals 0. Remember, we did some problems like that, where both top and bottom equals 0. What does it generate? Oh, or equals 0, sorry, they're both equal to 0. What happens when they're both equal to 0? You get out and define things, but what features do you have in the graph? Hold. The point is continuity. Yeah, removable discontinuity. So this would be, say, f of x equals, say, x minus 3 over x minus 3, x plus 3. So what number makes top and bottom 0? 3. So now, what's the complication with this? So think about this function. If you have any number other than 3, what happens to these two? Yeah, they're going to cancel. So those two don't affect the graph, except at 3. And what they do at 3 is they generate a hole. So your graph might have something that's going along, and then you graph at a hole like that. If it has to be a quadratic. So this is where we generate the holes. It's when the numerator and denominator equals 0. What is the last one of these? So we did p of x equals 0, a of x does not equal 0. They both equal 0. What's the next one of these? So p of x does not equal 0. So p of x is not equal to 0, and A of x does equal 0. What does this mean for the function? What would happen if you had 0 on top? So if you plug in 7 here. Yeah, the whole thing equals 0. So we generate zeros. So if I'm going to put a line across here to make it clear where we're switching things. Which means we get a 0 at x equals 7. That means when you plug in 7, the graph is at 0. So this is a way of finding where does the line cross the x-axis. So if you're doing it, this would be 7. So we might have a graph that looks like that. I don't know, whatever. This is how we're finding that point. Where does this top equal 0 if the bottom does not? Now what happens if neither of them equals 0? Nothing interesting is happening there. You don't have zeros, you don't have discontinuities, it's just a function. So I'm not going to even write that if they're both of them don't equal 0 because there's nothing interesting going on. So the question, if we are at a quiz or test, could look something like this. So say y equals say x minus 3, x plus 4, or plus 4, x squared minus 9. Okay, tell me about it. Where horizontal asymptotes are, vertical asymptotes, poles, anything of that sort for this graph. What might be the first thing you want to do, B? Okay, back to the bottom. What do you get? So, x plus 3, x minus 3. Okay, so horizontal asymptote. Where's it going to be at? So so we're comparing the power on top and power on the bottom. What is the power, if we multiply these out, what do we can have on top? X squared plus whatever. On the bottom we already have x squared plus whatever. It is not going to go to 0. 1. Why is it 1? Yeah, it's inverse. If they're the same, you take the coefficient 1 divided by 1. So y equals 1. You see it?
No, I didn't see the other.
Okay. There was only one x. Okay, that's it. So remember, when you see this, you would have to multiply them together if you were sure. So if you had to say a 2 here, notice it'd be a 2x squared. Okay? So this tells us horizontal. Where are vertical asymptotes? I'm going to put horizontal A, vertical A. At x equals where? -3. Would positive 3 be 1? No. So hole. Where would we have a hole? X equals 3 and 0. So x equals -4. So to get each one of these, to this, we compared the powers. So that's where we got this one. To get x equals -3, we just looked at that right there. To get x equals 3, I already used that color. X equals 3. How did we get that one? Top and bottom. And then to get to -4, we looked at that. Does that highlighting help point out where these are coming from? So we're looking at this, we need to be able to say each one of these parts. And if it's not factored, you probably the first thing you want to do is factor it, both top and bottom. Yeah. There could also be questions that act in the reverse. What do you mean by in reverse? Yes. So instead of like this, we say at the horizontal asymptote at y equals 2 vert asymptote x equals 1, x equals 7, x equals -3, whole x equals 5, and no zeros. So how would you do this? Let's start. F of x. I would suggest do this one last because it's the easiest one to adjust around because all we have to do is do plus or minus k, something like that. So how do you get vertical asymptote at x equals 1? Okay, on the bottom, what do we need? X minus 1. Because then if we plug in 1, we're going to get undefined. Okay? Then we can do x minus 7, x plus 3. Okay, that takes care of all three of those. How about this one? X minus 5 and x minus 5. Okay, now, if it just looks like this, where is the horizontal asymptote? It is 0, because the power on the bottom is going to be bigger than the power on top. So we've got two different ways we can do this. Probably the easiest way is to do plus 2 here. What would be another way of doing this? That's actually a bit more challenging. I'll show you. If we didn't want to do the plus 2, which of course is the easiest way, you could put a 4 here and put a 2 here. Why does that do that? Yes, it matches the power on the bottom. However, it does not add any zeros into it because they're all the same. But then I have the coefficient of 2. So that would work. However, the easier way, and probably the way you'd want to do it, is put a plus 2 out here. So again, if we want y equals 2, note we're getting from that, and I'm going to just put this to represent your exponent. Notice the exponent on the bottom is higher, therefore we just have to add the 2 to get it to 2. If we wanted x equals 1, we'll put x minus 1 here. 7, x minus 7, and if we want that, goes those 2. Okay, questions?
What if one of the variable asymptotes, what if there was only 2 of them? So what if it was only x equals 1?
So instead of like this, instead of like that? Okay, what would change? It would just get rid of that.
But what about when you put the 4 as an x negative x minus 1?
Okay, then you want to put a 3.
It can still work?
Yes. No, it is just, we have to match the power top and bottom, and then have the coefficient of 2. So basically we have to go back and be using this rule. So we've got two options, either use that rule or use this rule to do that. Now, anybody confused about how we're doing these? Because if we were doing a quiz tomorrow, this would be on the quiz. And on the test that's coming up, this is definitely on the test. Okay, one more type thing we're going to have on this homework. Solving 6 over x minus 3 minus 4 over x plus 2 equals 12 over x squared minus x minus 6. What do you have to do when you're solving a problem like this? Yes, you have to have common denominator. Now, before I do that, I'm going to put one thing up here. First factor this. What is the factor of? How convenient, right? Now, what numbers do we know cannot be solutions? X cannot equal 3? Why not? Because we get a 0 here. What else can X not equal? Now, I like to put those right at the beginning. That reminds me at the end, if I get an answer that says X equals -3 on this, or X equals 3 on this, I would know immediately that's not a valid answer. Because it will not work. So, what do I have to do to get the common denominator of this one? So X plus 2. Top and bottom. Why am I allowed to do that? Yeah, what's X plus 2 over X plus 2? 1, except at this point. That's why I put this up immediately, because then I can ignore it. Here, multiply by X minus 3, X minus 3. Now, the easiest way to go from here. Completely ignore the bottom. So you have 6, X plus 2, minus 4, X minus 3, equals 12. And this is now your Algebra 1 type problem. What are you going to do to solve it? Okay, so you're going to distribute out and then combine. So you're going to have 6x plus 12 minus 4x plus 12 equals 12. 6x minus 4x, 2x plus 24 equals 12. 2x equals -12, x equals -6. Anybody see what we did? Yeah. Once you get the answer, check it with what we had right here. Is x equals -6 a valid answer? Okay, so given that these are the two things we can't have, this is the correct answer. And of course we can plug it in to test it. But assuming we did all the math correctly, don't even really need to do that. Assuming we could check, make sure we don't have a domain issue. Yeah. Yes. The reason is when you add fractions, once you match this, it doesn't matter. So think about this. If we had 2 over 3 plus 5 over 7. Now, once I get the denominator the same, what am I going to do to get that? Times 7, times 7, times 3, times 3. I can now treat the top as just 14 plus 15 without worrying about the bottom. So, is the denominator going to have any effect on it in the long run? When we're solving, no, because our goal is finding what x makes it true. What number can we plug in for x? So think about what this would look like after we did this. If we didn't ignore the denominator, move this out of the way, that's clear. We would have this over x minus 3, x plus 2, x minus 3, x plus 2, x minus 3, x plus 2. No, I can multiply everything by x minus 3, x plus 2, and it all cancels. So just like if we had a number like 4 down here, what would I do to solve it? Multiply everything by 4, right? And then the denominator didn't do anything. Did you follow how that works? Now, what we do have to watch is this part right here. Our two problem child on the denominator. Because if we had a 3 as an answer, that would be running into a problem, because that wouldn't work. That's the reason I put this up here. Because if I ignore the denominator, I have to make sure I keep away from those two numbers, or whatever numbers those are.